our next presenter is going to be Mike Stolarchuk from BigSwitch. He will talk about BigSwitch, Big Monitoring Fabric, and DPDK. He is member of technical staff at BigSwitch Networks. He grows tomatoes and various peppers. I don't know how to pronounce these peppers' names, except scorpions. He repairs cars as necessary and feeds cats on request. And I was just talking to him a little bit before the presentation, and he said that he also drives 30 hours to get here.
Is it working now? Can you hear me? All right. So my name is Mike Stolarchuk, and I work at BigSwitch. I'm a developer there. And tonight, I'm going to talk to you a little bit about how BigSwitch uses DPDK in its products. Before I get too far, though, I want everybody to know that I'm a big fan of DPDK. It's a real enabler for the types of applications that I want to build, ones that are high performance, that try to get a lot of the OS out of the way so that I can get to the resources that I want. I also like DPDK because it's a toolkit, not a huge toolkit. It doesn't try to solve all the problems, but it solves enough of it that it enables me to be able to build the applications that I want. So tonight, first I want to give you a big outline of what I'm talking about. BigSwitch has several products. The one that I'm talking about is called BMF. BMF stands for Big Monitoring Fabric. Unfortunately, though, I like the old name of this product better than I like the new name. The old name was called BigTap. So what I want to do tonight is first talk about what SDN means to BigSwitch, or how BigSwitch implements SDN. Then I want to talk about what a network packet broker is, because BMF is an instance of network packet broker. Then I want to talk some about BMF specifically. After that, I'll talk about DPDK and what BMF calls service nodes, which is an extension to the architecture. After that, I want to focus on some issues that we had in using DPDK to build a solution. After that, I want to talk about a particular use case that we have where we use BMF to do our own performance analysis for the DPDK appliances that we build. If there's any questions, feel free to interrupt. There'll be a question and answer section at the end of this, but I'm fine with being interrupted whenever. So SDN looks different to a lot of different organizations. So I want to give you a picture about what SDN looks like at BigSwitch. In particular, what SDN looks like to BMF, but the same sort of model is used for all the products that BigSwitch has. At the core, we have this controller, the BigMon controller, which is an appliance in its own right, and it runs software which manages the configuration of all the switches that are actively connected to the fabric. So down in the lower corner, I have I wish I had a little pointer, but here, I'll use my finger. Those things in the bottom with the two arrows in each direction that's our picture for a switch. And so the controller has a TCP connection to each of the switches in the forwarding fabric. And as the controller gets updates for configuration that it manages, it changes the active state of the switches so that they reflect the forwarding model that is configured on the active controller. The thing that's important here is that those connections are on a management plane, not a data plane. And the data plane at the bottom is where the traffic moves from, at least for the big monitoring fabric, from left to right, at least conceptually, from left to right. So what's a network packet broker? Well, in the old days, when I started playing with networking, they had this thing called spanning. And what spanning was is you logged into a switch and you said, I want all the traffic that's coming in and out of this port to be sent out this port over here so that I could TCP dump it or send it to some tool for doing IDS analysis or whatever. And that's a reasonable model, but imagine now that instead of you having a single switch, you've got an enterprise that has 100 switches, and each one of them has a span port on them. And now you want to take all the traffic from all those switches and send it to a bunch of different services. That's a configuration nightmare. So what Network Packet Broker does is it provides you with a place where you can describe how you want this traffic to be managed. So you want the traffic from this switch sent to this port because you're, for example, running Snort over there, and you want the traffic from that switch sent to that port because over here you're doing recording on all the traffic, and you want all of the traffic from this port sent to this tool over here because you're trying to analyze your application's behavior. So that's what a network packet broker is. And there we go. Every application, sorry, every organization has substantial needs for monitoring. So here are some examples of how people use sophisticated products that are available from different vendors to meet specific requirements or needs that they have in their organization. For example, you can use a network packet broker to direct all the traffic to something to do application performance monitoring, in which case you're trying to figure out how well your application is working. Or you could forward it to something that does network performance monitoring to figure out how well your network is working. You know, traffic management. Are my links oversubscribed? What's the traffic on these links? Or you could take all the traffic that you're collecting and you could send it to a tool that's doing security analysis because you want to know if your machines are being broken into. I believe that the customer experience monitoring certainly sounds to me a lot like application performance monitoring, but that may be more focused towards what the customer experience as opposed to what the application experience. Finally, you may want to have tools for doing traffic analysis, you know, net flow, to characterize your traffic or to understand what your traffic patterns look like to possibly optimize or improve the behavior of the particular network that you're using. So the point that I'm making is that in every organization today, because of these issues and others, for example, HIPAA, there's a high demand for network packet brokers. And BMF is an example, or the big monitoring fabric is an example of a network packet broker. BMF is interesting because what it does is provide the user with a place where they can configure the behavior of all the sources and destinations for their traffic. So they can sit down and say, I want this interface, TCP port 22, all that traffic I want sent to this destination. And, and I want that same traffic from this other interface, also port 22, to be sent to that destination. So in a single place, you can sit down and you can view how the traffic is moving from all of the sources to the destination. So all the policies are configured to the controller. Equally interesting from my perspective is that all this configuration at the controller is done through a REST API. Both the CLI that we have and the GUI that we have use that REST API to perform all the configuration. That acts as a proof that we're not trying to provide magic interior configuration that's not reachable by some other application. Or what I mean by that is you can actually write a small piece of Python code to describe how you want the traffic to come from all the various sources and to be destined to all the various targets. Also keep in mind that BMF is interesting because it manages all of these switches all the time. And when I mean all the time, it also includes the life cycle for the switches. Whenever you upgrade the controller, the switches are also upgraded, and the versions of the software that run on the switches are validated to be correct against the version that's running on the active controller. So that was our picture for what BMF looked like. And in the architecture that we had, the switches that we were using are just commodity switches. So it's white box switching. And when you look at some of the requirements that customers have for a network packet broker, they include various feature requests that are very difficult to implement on top of switches. They include, for example, slicing, which oddly enough seems like a straightforward operation, but identifying where the L4 payload actually starts in a frame is something that switches really don't care much about. So because of that, they don't implement these sorts of operations. There are also much more complicated operations that customers want on top of their network packet broker, and they include operations like dedup, requests for services like IPFix and NetFlow, and also TCP connection tracking. So let me talk about dedup for a second and why it's important to a network packet broker. Imagine that you're sitting in an organization and you have a collection of switches. I'm just going to say some arbitrary number like 10. And those switches are wired so that frames travel between them in your organization. And you're spanning those ports to some central network packet broker. So happens that if a packet transits east and west, the network packet broker is going to see 10 copies of that packet, 10 distinct copies of that packet. And if your destination is a complicated, expensive tool that whose cost is based on the amount of traffic it receives, you're now paying 10 times more than you have to for the cost of that specific tool. So what dedup is doing is it's removing the excess copies of those frames as they transit to the destination. This is obviously an optional sort of service that you may or may not want to include depending on what you're trying to do with that traffic, but certainly in some instances it can help lower the cost and also simplify the traffic flow that you're collecting through the packet broker. But unfortunately, switches have a tough time doing dedup. And the reason is because it takes a substantial amount of state to be able to figure out whether or not you've seen that frame before. So to deal with that problem and other problems, we decided to extend the BMF architecture to include things other than switches and controllers. In particular, we wanted to focus on commodity servers, X86 machines, and we wanted to run DPDK on top of them because we needed to be able to manage 10 gig fully saturated links on these machines. The expectation would be that if I'm doing network packet brokering, the data comes from a source and goes to a destination. There's no opportunity to do flow control. Because of that, these servers need to be able to do processing at as high of a bandwidth as we can get them to work. Additionally, we have some other properties that we want to make sure get included in these DPDK devices that are extending the architecture. One of them is that we want to, again, use OpenFlow as we already used to talk to these devices, just as we talk to the switches, to manage them so that they're not separate entities, but part of a larger solution. Finally, what we also want to do is plumb these x86 servers into the fabric in such a way that the controller can completely manage all the data that's moving to these devices and to redirect it once it comes out of these devices to send it towards some endpoint. So here's the big picture of what the service node looks like in our architecture. So we have traffic that comes from, so that the top with the two arrows, that's a switch. The bottom is a service node, and that service node has an interface plugged into that switch. To process a frame in that service node, the frame comes from the switch, it enters the service node, some activity happens there, it gets hairpinned out that same interface, goes back up to the switch, and then the switch gets to process that frame as it sees fit. So one of the novel parts of this description is that the service node is only ever plumbed to the switch and nothing else. And the controller manages all of the sources that get fed to the service node, and it redirects all the traffic wherever the configuration of the fabric has decided towards the destination. So it's not the case that we're plumbing this service node some endpoint. We provide it as a tool that can be used generically across the board for any one of the traffic patterns that exist in the forwarding fabric. Any questions? Got that? Yeah.
Can you send from one node to the other, service node to the other?
When you say one to another, are you saying if we had two service nodes that are adjacent, can we forward them between each other?
Right.
And the answer is yes, we can. I'll give you an example, but the idea is, let's say you had a service node and it had a collection of interfaces. Well, I'm just going to pick a number, like 4. So since the switches are directly connected to the service node, traffic can come into one of the ports, be directed down to the service node, be directed back out, and then the controller can redirect that traffic to go down to the very next port in the service node and perform an additional action. Another question?
So you are using a service node because the switches didn't have a consistent way of an ER span.
So we don't actually use, what are you using ER span for in your organization?
I haven't used it. I just
Do you mean just for the sake of collecting traffic?
I'm just thinking that why is that you need an extra node, because that node becomes the bottleneck for the amount of traffic that can really be monitored.
Well, it depends,
the switch itself,
right?
it can do whatever.
So there's a question about bandwidth there. So what's the bandwidth limits of this physical device? So part of the bandwidth limits are a physical issue. For example, it has 10 gig interfaces on it. Another limitation is obviously the amount of traffic that a particular service on that particular machine can handle. I'll give you an example of a complex service, a regex. So if you were to do regex pattern matching on frames that were destined for the service node, it's difficult to do that at 10 gig only because of various complexities associated with big regular expressions. So if the question is bandwidth, then you could take and lag the traffic over multiple interfaces on the service node to do lossless regex, as an example. Yeah, other questions?
Can a single service node be used by more than one switch?
There's two answers to that. Because a single switch can only be connected to a single controller, then that switch is managed, and that service node is managed by a single controller. If the two switches are both managed by the same controller, then the service node can span multiple switches. It makes perfect sense, right? Any other questions?
Question is, what's the purpose of sending it back to the switch, and what kind of action you're taking inside the service node that the switch can't do?
Instead of what?
I mean, what's the purpose of sending it back to the switch? That's number one.
Okay.
Only if we are monitoring the traffic, right? So we can do the monitoring by two.
So let's talk about, that's a good question. The answer is why are we returning the traffic? Imagine that the service that we're doing down here on the service node is dedup. So dedup is going to behave as follows. We have a frame that comes in through 1. It gets sent down to 2. And 2, the service node records it as a frame that it's seen. It then takes that frame, because it's never seen it before, and it forwards it out and sends it up the fabric. And the switch behind that interface now decides where that frame goes, possibly to snort, possibly to an analysis tool, but it's directed by the controller. The service node doesn't care where the frame goes. It's done its job to dedupe the frame. Second frame comes in. It's the same. It's a copy that the service node has already seen. The frame comes in. Now the service node sees that the frame was received. It now drops that frame and doesn't send it out the interface. So the behavior of the forwarding of that frame from 2 to 3 depends somewhat on the action that you're performing on the service node. Imagine, for example, that you're doing slicing, where all you're doing is you're chopping off the end of a frame. In that case, all the frames that come in get returned, get hairpinned out. But the frames that are hairpinned out are now just truncated compared to the original frames. So this provides a lot of flexibility in the architecture for the controller to be able to manage exactly what behaviors it wants to do on exactly what data stream. Does that help? That's correct. Unfortunately, though, it's sitting on the data plane, not on the control plane. Yeah. Okay. Ready for the next?
So, quick one.
Sure.
Here.
Sure.
Just to, I think you sort of answered my question. Now, is this service node is basically like essentially a controller or data plane add-on for processing, extra processing?
That's exactly what it's doing. It's dealing with limitations that exist in the switch. And because the switches have limited capacity, they're not meant to do things like dedup. They're meant to do forwarding.
Yeah, and that's why you're extending.
That's right. And we're extending it, but we're still embracing it in the architecture. We're using OpenFlow to configure it. We're not letting it be a component that people log into. It's a slave component that has responsibility based on how the controller directs it to behave.
Do you see this as a caching device or something like that for dedup example? I mean, would I be...
When you say caching, I'm not too sure what you mean.
So, like, basically, if you're deduping the packet data that's coming in, typically what happens is there is somewhere, there is a source packet that's getting sourced out. Do you expect, or actually, do you see a use case where the service nodes will act as a caching? So you don't have to go to, like, in a WAN caching, basically, like, for example.
That's an interesting idea. I haven't thought of that. I can give you an example of where the service node is doing caching. It's a feature that we haven't implemented yet, but we will at some point, and it's as a latency provider.
Yeah, there you go, yeah.
Because in that scenario, where if you're doing some testing and you have a requirement where you want to simulate a really long path, but you can't afford a really long path, you'd like to inject latency. And really what latency is you're caching the contents of a frame for a duration of time before you retransmit it out the endpoint. Yeah. So we have an application that we've written in DPDK to do that. We just not integrated with the service node behavior. So latency would be an example where caching is valuable and provides a useful resource for doing certain types of testing, but we just haven't set it up to do that yet.
Makes sense. Thank you so much.
Yeah.
Okay. The question is, you mentioned the difficulty of doing 10 gig or 10D regex.
Yeah, right.
Have you looked at Hyperscan to accelerate our pattern matching? It's open source.
No, we haven't. Instead, we use just-in-time compilation on some of the various regex libraries that exist today. Okay? So I want to look at the service node again, but this time from a different perspective. I want to talk about how wide it is, because what we talked about so far is you have a 10 gig interface, traffic comes in, traffic comes out. But you know, a single 10 gig interface, that's not very interesting. We're trying to, we already have as a product a 16-port service node. And on the 16-port service nodes, you have 16 gig, 10 gig ports, with each of which can have a distinct service that runs on top of it. All the traffic goes in the ports, all the traffic goes out the ports, and it causes an interesting problem when it comes to topology. Because if you have 16 ports and you look at a switch, 16 of its ports have to go to the service node. Now, if you want to send useful traffic to the service node, you need to bring 16 ports into that switch to direct it down to the service node. And you also need 16 ports to egress that traffic. So really, a 16-port service node requires a 48-port switch to be connected to make it successful in a fabric. So here's what BMF looks like today. I have to apologize. This is a marketing slide. This is supposed to be a technical presentation, but it's a pretty nice slide, I think. So we have the controller at the top. We have a forwarding fabric. We have service nodes at the bottom. We actually are beginning to construct third-party service nodes, and we're now integrating analytics. So really what we're looking at is it's not really a big monitoring fabric. It's more like a big monitoring solution, because it includes not only the fabric, but the configuration that's done in the controller also coordinates the configuration on all these various associated services. So, that's very nice. Better slide than I thought. So here's, again, focusing on the controller. The controller is interesting because it's, as I've mentioned, it's a single pane of glass of management. It's a REST API. It's resilient. We have HA in the controllers. I'm not interested in that. But the advanced telemetry and analytics is another example of an extension to the service that's different than the service node, but it underscores the fact that we're moving towards an architecture where we're not building a fabric, we're building a solution for the customer. We're doing that using commodity switches, white box switches. We run our just own distinct software on those switches. And this is a service node. This is actually why I had these slides, because I wanted to put this one up. So the service node is a commodity X86 device. There it is on top, commodity. And so this is an example of some of the collection of services that that particular service node can do on any one of its ports. Deduplication I've mentioned, slicing and masking, various header decaps, regex and DPI filtering, netflow generation. We're currently working on IPFix, software-based timestamping, and we're currently working on GTP correlation. These are all implemented on top of DPDK. Now, I showed you the picture. Back up a second. There it is. There's a picture of commodity server. I got to tell you that as much as I like DPDK, I'm not so thrilled about the various challenges that were caused by the use of commodity servers. They're not really meant to be used this way as a switch, essentially. They have these front-facing interfaces. Sorry, they have these rear-facing interfaces, not front-facing interfaces like a switch does. So they're difficult to plumb, and it's really difficult to figure out which one is port 0. Additionally, we've had problems with commodity servers because a lot of the manufacturers, they won't tell you where all the PCI devices are plumbed, which processor, which lane, because it's typically not important for most use cases, but for our use case it is. And of course, another problem that we have is just the availability of good high-performance NICs. Now, that's just to underscore that that's not a DPK issue, that's just a manufacturer issue. There's really not lots and lots of good choices of high-performance NICs. Now, what do I mean about the labeled port issue? Well, here's the 16 ports on the service node, and here's where port 1 is and where port 16 is. So one of the challenges that we have is communicating to customers that the commodity servers really don't provide you with an easy-to-understand plumbing. And because these are backwards-facing ports, and because the switches that we want to plumb these 16 ports into are all forward-facing, you've got sort of like a twisted bunch of cables that go from the back of the cabinet to the front of the cabinet. But, you know, these are servers, and that's really how servers are built. So the commodity servers are a great solution because they're easy to acquire. We can validate specific, we can verify that specific servers actually meet the requirements that we have for performance, but we have lots of problems in identifying specific platforms and solutions that work for this sort of density. We also have problems when it comes to resource management. Now, this is a different issue. It's not, I'm not talking about the application getting enough CPU cycles, and I'm not talking about the application getting enough memory. I'm talking a different type of resource management. As an example, I want to remind you about the dedup case. If you have 16 ports and they're all doing dedup, you don't want one of those cores that's doing dedup interfering with another core that's doing dedup. And what that really means is that you can't have those L3 caches interfering with each other. On our product, we used some of the neat Intel features for doing cache management. But the cache management feature has limitations, which have an impact on the scale that we can drive these server sizes out to. So one of the problems we have is L3 management. Another one we have is CPU frequency management.
So Mike, the cache management features you're using is RDT?
Let's see if I can get this to work better. Is that better? Yeah, I think that's better. So what was that question?
Are you using RDT for cache management features?
Oh, no, I'm not. We're using the Intel library for managing CMT and cache.
That's resource director technology.
So resource director technology actually includes CAT and CMT as part of it as well. So that's what she's getting at here.
That may be true, but I think what you're talking about is the Linux variation. Is that correct? Is that the Linux implementation, or is it?
It's a hardware feature. And
okay.
You have API.
Oh, so you mean resource management? I call it CMT cap because that's the name that I had. The resource management is the new name for the same feature.
Right. Yeah.
Now, so L3 management is a big issue. One of the reasons it's a big issue is because it isolates the cores from each other so that when we're doing activities in one core, it won't affect activities in another core. Another problem we have with resource management is CPU scaling. Over time, the cores have gotten smarter and smarter. And unfortunately, that means I have less and less access to be able to tell it exactly how I want it to behave. So when we're doing performance measurement, sometimes it takes a while for the processor to ramp up to full speed. And it's difficult to find good APIs to be able to tell the processor just to stay at a stable clock rate, the highest available clock rate, but to stay at available clock rate. So aside from processor-based resource management issues, we also have problems wrestling resources away from Linux because our solution runs on top of a Linux platform. And DPDK is meant to run on that platform. It's well suited for that. we have all sorts of issues. One of them is memory. We really don't know exactly how much memory an application can acquire before DPK stalls forever, as an example. So we're conservative in memory use in a DPDK application where we'd like to be less conservative. Another issue that we have with resources in Linux is getting the scheduler out of our way, because we want full control of all the cores that are doing forwarding to lower jitter. And, good news is that Linux has some mechanisms to do that. ISO CPUs, no hertz full, and there are mechanisms for telling the scheduler that you don't want it to interfere in the way that you're controlling all those cores. Obviously, we're going to remove IRQ balancing so that we only see interrupts on the processors that are not doing data forwarding. And one of the final sources of jitter that took a long time for us to identify was NUMA rebalancing. Because every time there was a NUMA rebalancing event, all the page faults forced jitter in the forwarding of the cores. So resource management is a struggle, and one of the problems is there's really not a lot of discussion about that on any of the mailing lists or any of the DPDK information that's available. Another problem that we have, another challenge, is that it's really difficult to characterize performance of applications using DPDK. DPDK runs the processors at full speed, never any idling. The processors are always doing something, even if it's nothing. Typical tools that we have for doing analysis of applications depend on having the application identify when it's idle, so that those spans of service are not part of the measured process of the application. One solution is then to run the application at 100% and take the measurements, but that's really not a great solution. We're still looking at various ways of dealing with the performance measurement aspects of DPDK applications.
Have you used vTune for that?
No, I haven't. That may be a reasonable. Yeah, I'll talk to you about that afterwards. So the biggest challenge that I have, though, with DPDK is really trying to identify whether you're getting all the performance that you expect, or if you're getting the maximum amount of performance that you could get out of an implementation. That's very difficult to do because there are various bottlenecks that can, stumbling blocks, that can prevent you from getting to that best possible performance. One thing that we do, for example, is rerun on the machines that we have as validation, rerun hairpin tests at 10 gig at minimum packet rates to make sure that the hairpinning works at full bandwidth at minimum packet sizes. So that's one of our first base tests that we run. But at the same time, I also want to talk about a different strategy that we use for validating the performance of the service node, and it uses BMF itself. And I want to talk about this. There's not a lot of, this will go pretty quick, but it's sort of interesting. Imagine that you have a controller, and you have a switch, and you have all these APIs available to you. And on the left-hand side over there, you have a service node that is generating traffic, and on the right side, you have a service node that's going to receive traffic. Here, I'll trade you. Let's see, does this work? Yeah, that's actually, it sounds like it's easier. So I have this application, and the application is written in Python. It's about 1,000 lines of code. Here's what the application does using the APIs on our platform. It talks to the controller, and it asks it where the service nodes are connected topologically, which switches they're connected to. Once it figures that out, then it creates a policy where it tells the switching fabric that it wants to take the traffic from that interface on that service node and duplicate it 4 times to this service node. And the reason this is interesting is because now I know that the traffic that's being sent to this service node on the right is exactly the same for all 4 interfaces. Then what I do is I configure the right service node to tell it I want a dedupe on all its ports. Then what I do is I tell the traffic generator on the other service node to send traffic out that one port. Then I analyze all the counters after the test is over. And because of that, what I can do then is iterate starting from large packet sizes down to small packet sizes until I see packet drops, because some of our metrics for all of these interfaces on all the switches and on the service node, they include packet drops. So the application can tell whether it's seeing packet drops on the transmit side on the switch, or if it's seeing packet drops on the receive side on the service node, or if it's seeing packet drops on the transmit side on the service node. So here's an example test. This is run on a E5 2650 V4. This is a pretty nice machine. The first test on the top is a 2-interface test. So the service node is only running dedupe on 2 frames. And this is doing a search down to find the minimum packet size before packet drops occur. And for the first test, we actually get down to 64-byte frames before we see any loss. On the second test, I have 4 interfaces loaded, and the 4 interfaces are running, and the minimum packet size that I see before I see packet drops is 101 bytes. Now, I know why it's 101 bytes and not 64 bytes. And that's because of the physical interface that I'm using. It has a limitation. The physical NIC can only handle so many frames per second before it starts stopping frames. And so what I'm seeing in this second test is not really the bottleneck is not the dedupe rate at the service node, but rather it's the physical NIC that's causing me to drop frames. So here's my big takeaways. Using DPDK, we've extended the BMF architecture to include new things called service nodes, which are DPDK appliances. The controller manages those appliances using OpenFlow as if they were switches. We use DPDK to squeeze all the performance out of these service nodes. And we put APIs everywhere, APIs that are easily available so that if you want to write that Python script of 1,000 lines, you're welcome to do it. Any questions? Yeah.
So it looks like a DPDK protocol only helps to speed up local data transfer instead of, like a long distance transfer. My question is, a lot of data ingestion systems like Kafka, will they implement a zero copy sort of mechanism? So it's very similar to DPDK protocol.
Actually, DPDK is very different than a zero copy protocol.
Very different?
Yes.
But anyway, I mean, the goal is the same, right?
The goal is the same.
The goal is the same.
The goal is the same.
So for the infrastructure or a sort of a cluster, or they using Kafka, what is the key difference in terms of performance and cost?
I wouldn't be able to. I don't know much about Kafka, so I can't really do the comparison. If you want to talk with me afterwards, we can probably come to some conclusion.
Okay, thank you.
Yeah. Anybody else? Yeah.
You have shown like 2 level of negotiation, like first from switch to DPDK or service node, and then you're saying controller configures the service node.
That's correct.
So if something service node doesn't understand about the frame that comes from the switch, does it like go to the controller? No,
because when you say doesn't understand, the model that you have is that the service node is a switch.
Right.
So we have to back up for a second and recognize that OpenFlow is a protocol that has 2 properties associated with it. The first is that it's a way for communicating configuration information and statistics to the switch. But the second is that it embraces a model of behavior for the switch, right?
Right.
Includes flows. Imagine that you didn't have flows.
Mm-hmm.
And you had just the need to do configuration on this endpoint, on the service node.
Right.
So it's not behaving like a switch. It's just behaving as a configurable entity as part of your architecture.
Okay.
Does that help?
Yeah.
Yeah. Yeah. So what type of hardware acceleration? Oh, sorry. The question is, would it be possible to use hardware acceleration to improve the performance of the service node? So it's not clear to me what type of hardware accelerations we're talking about. Examples of hardware acceleration could be the AVX SSE instruction set, because those are specialized hardware features that exist on a collection of x86 machines. If you're talking about specialized hardware that's not on the x86, I'm completely not in favor of that for a variety of reasons. The first is that Intel rolls out a new processor every 18 months. And typically, the manufacturers of specialized hardware don't have the budget to be able to do that. So over time, the x86 just swamp out the specialized hardware devices. So we focus instead on trying to figure out how to squeeze the performance out of the Intel machines to meet some of the performance requirements that we have. Yeah.
Two questions. And the first one is, like, when you said you had a 10-switch network going east to west, and they are controlled by the same controller, how will you do deduplication in that case? Isn't each switch giving its own packet to its own server node?
So in that picture, and so let me repeat the question, how do you manage dedupe in a situation where you have east-west traffic with a collection of switches that are managed by the controller, and you have this requirement for deduping the frames? So conceptually, you have to separate the forwarding switches from the network packet broker. The forwarding switches, imagine that you had some product that could do forwarding for your enterprise, like maybe BCF. And so you have a collection of OpenFlow switches that are managed by a controller that's sending traffic east-west for your enterprise. That's a solution in its own right. What you want to do then is have specific tapping points from that topology into the network packet broker. So you're going to span various ports, or you're going to put some form of collecting the traffic so that it comes into the network packet broker, so that then you can describe how you want that traffic managed. It's a good question.
Second question was, on the service node, can you do more than one function on the same packet?
That's a really good question. So we actually limit the number of actions that we can do on an interface, primarily for the simplicity of the understanding of how the customer is consuming the resources on the service node. The service node is actually completely capable of doing multiple services on a single interface. And in fact, it's capable of ganging multiple services together and segregating them by inbound VLAN, as an example. Those models, though, are a little bit difficult for the customer to consume in terms of complexity. So we've stepped back from that issue right now, and at some point, we'll figure out how to embrace a richer configuration style. Okay? I think.
Okay, one last.
Okay, last question.
So, a lot of protocol actually has its inherent weakness. I'm just curious, how much is DPDK protocol being cluster aware? Cluster aware?
Cluster aware?
Yeah.
Cluster aware? So keep in mind that DPDK is an API and not a protocol. So it's a collection of tools that help you better implement a particular solution. And the good news, at least from my perspective, is that DPDK doesn't really provide you with a lot of magic tools for managing NUMA, but it gives you enough of the tools so that an application that you write can decide how it wants to associate, for example, memory with various NUMA sockets. That's correct.
You provide API, DPDK per API, but that's relying on the chip has been DPDK enabled. Zero copy or sort of similar mechanism has been implemented in hardware. So the protocol itself has been in hardware.
You mean, for example, RDMA?
No, yeah, I mean, yes, zero copy. I'm talking about the disease kind of mechanism. So of course, we are programming using the API. So I'm talking about whether the underlying protocol or sort of API is that a cluster aware or not? Cluster aware. You mentioned that there are certain weakness in terms of scheduling, resource allocation, right? That's why I'm asking, is that a cluster aware or not? Yeah.
Well, given that DPDK doesn't try and solve any cluster-based issues, it's difficult to see that there's necessarily an issue there. I think if there were high-level applications that needed to deal with some cluster awareness, that it would have the responsibility for managing where the particular operation takes place. Thank you. Okay.
Thank you, Mike. That was wonderful. So time for a little break before our next presentation by Elango. Michelle, can we have the idea roll as well? So there's a 10-minute break, and you can use that for bio break. But before that, there is an announcement. So I talked about Intel Software Innovator Program